Hi, my name is Dr. Barry Flannery. I'm the founder and CEO here at Xerotech. Welcome to our latest series, XT Tech Talks, where we walk you through the very fundamentals of batteries right the way through to more complex topics from thermal management to fundamental cell chemistry. Today's episode is going to be the absolute basics, the fundamentals of energy, power, voltage, and amps. I'd like to give you a walkthrough of that so that you're well grounded in batteries. So let's get started and let's start to talk through a lot of the fundamentals of batteries, energy, and energy storage. So my background is actually applied physics. I have an undergraduate in that before I went on and did my doctorate in mechanical engineering. So what we're going to do today is to go through basically the laws of physics. The very first starting point to understand electricity, power, energy is a bunch of very simple fundamental equations. So we're going to start with one that everybody should know, which is V is equal to IR. What this means is the voltage is equal to the product of current times resistance. This fundamental equation is interchangeable, and by increasing the voltage, you'll decrease current. The second most important equation to understand is that power is equal to voltage times current. This second equation, power is equal to voltage times current, is incredibly important because a lot of people get confused between voltage and current, and high voltage, high current, low voltage, and so forth. The most important thing to understand is that it's a zero-sum game. And what I mean by that is the power will be constant. So if our power, for example, was 1,000 watts, where watts are the unit of power, to achieve that, you could have a voltage of 1,000 volts and 1 amp. So that's volts and that's amps. And per this equation, power is equal to voltage times current. Similarly, you could achieve 1,000 watts by having 1,000 watts, 1 volt, and 1,000 amps. These are both the exact same thing in terms of power, but more importantly, the difference here is the current. What's very important to understand about current is that it's very physical. So if you've got something that carries 1,000 amps versus something that carries 1 amp, it'll be a dramatically different conductor. And a conductor is something that carries energy or carries current, which is a unit of moving energy through something. So for example, a small little wire that might be in a charging cable for your phone, that'll be capable of carrying a few amps. If you want a cable that can carry 1,000 amps, it might be as big as this. So there's a dramatic difference between the voltages and the currents. When it comes to voltage, it's a lot easier to have higher voltages than it is higher currents. So for example, a few millimeters of insulation on a wire can provide thousands of volts of insulation. So there's not that big of a difference to go from 10 volts to 100 volts to 1,000 volts. It's a lot easier than going from 10 amps to 100 amps to 1,000 amps. So the big advantage of going to higher voltages is you can achieve higher powers with smaller conductors and lower amounts of amps. And you might say, why don't we make everything high voltage? Well, that's quite obvious. Most of you know that electricity can give you a shock. So something that exists in the world today is that there's generally a low voltage directive to stay below around 50 volts DC. So for example, in the car industry or forklifts and things like that, the systems are generally lower voltage. So if you've ever opened the hood of your car, you could probably see the battery, and it's a 12 volt typically, or sometimes 24 volt in trucks and bigger vehicles, lead acid battery. The reason you can see and touch those terminals is because the voltage is under this low voltage directive. So you can't easily get a shock off of that battery. Whereas if you see a high voltage battery system that's over this threshold or over a few hundred volts, all of the connectors are orange. You can't touch any conducting components because you could get an electric shock from that system. So that's the big difference. And I suppose there's an added cost of going to higher voltages. The conductors all have to be protected. There's more advanced safety and protection systems, but it comes at big benefits of being able to deliver much higher powers throughout the system. So in general, when it comes to amps, in all practical systems that we would deal with in a battery or in a vehicle, generally speaking, a few hundred amps is about the maximum of what will be allowable or standard in the market. So any electric car that exists today, at most would be delivering only 500 amps of power, regardless of the overall power that the vehicle needs to actually deliver. So if you take that 500 amps current limit, and if you have a car that needs to deliver, say, 300 kilowatts, 300 kilowatts, kilo is 1,000, is 300,000 watts. So basically, the only way you can deliver that amount of power is 300,000 divided by 500. You can quickly see that you need quite a high voltage to achieve this amount of power. The power requirements of these bigger machines, these higher power applications, it means that you have to be high voltage. So that's causing quite a big change in the market today, that a lot of the battery technology that exists historically has been focused on low voltage, where the power was a lot lower. So now as we shift to higher power applications, everything must become high voltage. The next most important piece when it comes to current, voltage, and power is this most fundamental equation that actually governs a lot of these wires and their size. So we're just going to clean this off and start afresh. Going back to our fundamental equation of power is voltage times current, there's a very important law of also heat generation, or the power lost, resistive losses. So it's actually power or energy is equal to I squared R. What this is telling us is that as current flows down a wire, it encounters resistance. And what's more important is that there's a loss, and that loss comes up as heat. Heat gets generated from the wire as the current flows down it, and it's a function of the current flowing through the wire. So what's really important here is that it's going up as the square. And what that actually means is that if you put 2 times the current through that wire, you're going to get 4 times the heat coming out of that wire. Or similarly, if you want 4 times the current, you're going to get 16 times the heat. Keeping currents down does a lot of things. It makes your conductors smaller, and it makes the amount of heat generation a lot lower. So modern electronics, by being at higher voltage, has less losses, less failures, less issues, because they're not having to deal with heat rejection. In fact, that's why you have to liquid cool a battery. That's why you have to liquid cool modern power electronics, is that largely you're trying to eliminate these efficiencies and these efficiency losses. So keeping the currents down is really important, and the way that's achieved is using high voltage, insulated wires to minimize that and maximize your power output. So now that we've got the fundamentals of physics understood, we're going to talk a little bit more about batteries and capacity. So to understand the units of energy, energy is like volume of water, it's like liters, it's a storage measurement. So if we say that the unit of power is watts, the units of energy is watts by time. Or very simply, if you've got a 100-watt light bulb, and if you run that for 1 hour, you will have basically consumed 100 watt hours. Or similarly, if you've got a smaller light bulb, let's make it very interesting, an 18-watt light bulb, run this for 1 hour, that's equal to 18 watt hours. So now that we understand what power is and what energy is, so the unit of energy is watts by time, let's start talking about batteries. So a battery cell stores energy. And what's interesting here is that a typical 2170 battery cell that most people on the market would use today has got a certain amount of capacity in it. We'll come back to what this means in terms of amp hours. It's a 5 amp hour cell, and it's probably got a nominal voltage of 3.7 volts. So when you multiply the capacity times the voltage, you get the energy. So 5 times 3.7 is roughly 18 watt hours. So this battery cell could power an 18 watt bulb for 1 hour, and then the battery is going to be fully discharged. So that's where batteries and energy come in. When we talk about amp hours, that's no different to talking about watts and watt hours. So what that means is that this battery cell contains 5 amp hours of capacity, or more simply, it could deliver 5 amps of current for 1 hour. And that leads to it being a 5 amp hour battery cell. So we're just going to clear off again and just get back to some more fundamentals. So now we're talking about energy and capacity. So energy is watt hours, capacity is amp hours. Now, the one thing to be careful of when thinking about batteries, and why it's always important to think in terms of energy, is the overall amount of energy in the system is the product of capacity times the voltage. It's very similar to our first equation of power equals voltage by current. Energy is equal to voltage times the amp hours, basically. So the reason this matters is that if you've got a battery that's got 5 amp hours in it, it doesn't tell you how much energy is in that system because you need to know the voltage. So every battery cell, a fundamental thing about lithium-ion batteries is that they're usually all the same voltage, typically. It comes from the chemistry. So the nominal voltage of a battery is usually around 3.6 or 3.7 volts, roughly speaking. And the battery will have a discharge curve that goes from 2.5 volts to 4.2 volts. That's the complete operating range. But its capacity will be fixed, it'll be constant, that within that range, it will have a total capacity of 5 amp hours. And then to understand the total amount of energy, it's just multiplying both of these numbers by each other. So as we said, when you multiply 3.7 volts times 5 amp hours, that equals 18 watt hours. So a 5 amp hour cell is around the best in class on the market today for energy storage in a battery cell. It's around the highest energy density. The next generation battery cells are up on around 5.3, 5.5, even as high as 6 amp hours. So roughly speaking, for a 2170, you've got about 16 to 25 watt hours of energy in one battery cell. So while we're talking about the amp hours, the capacity, it's worth talking about something you might hear in the battery industry called a C rate. The C rate is a quick term to understand the discharge capacity of a battery. So we're going to just have to clear off our table again here to go through this. We're back to our battery again. This is our 5 amp hour battery cell. It's a 2170 battery cell, and its voltage is about 3.7 volts. If we say we're going to discharge this battery at 1C, it means we're going to discharge it at 1 time this, 1 times its capacity. So that will be the C rate. So that means a 1C discharge would empty that battery in 1 hour. If you're to do a 2C discharge, it's going to basically be doing 2 times this number. 2 times 5. So it's equal to 10 amps. That will be a 2C discharge. So if we know that there's 5 amp hours in it, and we're discharging at 10 amps, we know that we're going to have that battery fully empty in 0.5 hours, or around 30 minutes, and so forth. You can go up even higher. So if you have a 10C discharge, it's going to be discharging it at 50 amps. So that's going to be discharging it in basically 5 over 50. That's going to discharge in 0.1 hours. That's a very fast charge or fast discharge. So when we talk about batteries that are fast charging and they can charge in 30 minutes, if it's able to charge in 30 minutes, that means it's charging at 2C, a 2C charge rate, which is very aggressive for many different reasons. The reason these C rates matter, and we need to go back to the equations we used at the beginning, is that equation of I squared R. So if we go back to that equation, we find out that the resistive losses increase with the square of the current. So we're back to our fundamental here of I squared R, the energy loss. So this is basically the resistive loss. It's going up as the square of the current. So when we talk about the resistive losses here, it's going up as the square. So if we have 5 amps squared times 1 ohm, this is going to result in an energy loss of 25 watts. It's quite a lot of energy to be wasting for a battery cell that only has 18 watt hours. Now in reality, a battery cell has a much lower internal resistance inside of it. A typical internal resistance of a battery is probably about 30 milliohms. A cell like the one we have here. So that means the loss in that case is 5 squared times 0.030, which is a much lower value. So when you take 5 squared times 0.030, that equals to about 0.75 watts of loss, heat loss in this battery cell when you discharge at 1C. So that 1C would be quite aggressive. You're using up the battery in 1 hour. It'd be like driving an electric car and being out of battery after that hour, or a vehicle. So that's quite an aggressive rate. But what's important to understand is that it goes up with the square of the current. So let's say we wanted to do a 10C discharge. Not only would the battery be empty in 0.1 hours, so very, very aggressively emptying, the amount of heat generation will be equal to not 5 amps squared, but 50 amps squared, which is a much, much bigger number. So the 50 amps squared times that resistance will be equal to nearly 76 watts of heat loss generation, a huge amount of heat loss. And this is very important when it comes to battery packs because twofold. Batteries generate heat when they're being charged and when they're being discharged, largely because of this reason. There are some other things that contribute to the amount of heat generation in the battery that are not just simple resistive heating, electrochemical things, but this is the dominant source of heat. And that's fundamentally why you have to cool a battery cell, is to stop it from heating itself up to a potentially unsafe region. And it comes from these basic equations. So keeping the currents low is very important within a battery to make sure it lasts a long time. But similarly, when you design a battery pack, you want to make sure that the voltage of the battery pack can be a lot higher. So all of your conductors in the battery are not generating lots of heat because of this square of current. So the next thing we're going to talk about is what batteries are for, or what energy sources are for. Generally speaking, an energy source is to power a load or do some form of useful work. So we're going to clean our slate off again. So if we're to understand a really simple circuit here of just a battery connected to a light bulb in a circuit going around, and this light is generating, this is not exactly an electrical schematic, but what it's doing here is it's creating a flow of current through this light bulb and it's dissipating energy. So basically most traditional old types of light bulbs are just resistors. So this is a resistance inside of this light bulb here, R. And the amount of power that it's able to dissipate in generating light is going to be the voltage is equal to the current times the resistance. And the power is equal to the voltage times the current. So by using these two equations together, you can figure out how much power this battery can generate with that light bulb. So if the battery had 12 volts and the resistance was 1 ohm, you can easily work out with these equations how much current is going to flow. So if we take V is equal to IR, 12 volts is equal to the current times the 1 ohm. In this simple case, 12 amps is going to flow. And then to understand how much power might be dissipated, you simply take power equals voltage times current. So the power is equal to 12 amps times 12 volts is equal to 144 watts, which probably isn't far off a car headlight. So the voltages here and the resistances are typical for a car headlight. What's interesting to look at is for that same light bulb, 12 amps is quite a bit of current. It would need a reasonably thick wire to deliver that. If the voltage were to be doubled, you'd be able to deliver the same amount of power with half the current. So let's just understand the difference between AC power, the things that we all have in our homes, and DC power, the thing that comes out of battery packs. So when we talk about AC, we're talking about alternating current. When we talk about DC, we're talking about direct current. And what that means is that if we are to take an axis of how that current flows between going positive and negative, alternating current, if this is 0 volts, because it's voltage that drives current, and the peak of typically in Europe here, it's typically about 230 volts AC. That means that it's alternating from plus 230 volts AC negatively down, up and down in a sinusoidal fashion like this. And the current that flows will follow this sinusoidal wave. So it's going from positive 230 to negative 230. When we talk about DC voltages, DC is a constant voltage. It just is at a positive constant voltage of say plus 400 volts DC. And the current that flows will also be positive, and it'll be unidirectional. So it'll only flow one way from A to B, whereas alternating current goes forward and back. And the better way to think about it is an AC power circuit, it's closer to vibrating backwards and forwards as opposed to shooting backwards and forwards. And DC current only flows in one particular direction. One of the most important things to understand about batteries, about voltage, about AC and DC is voltage is a potential difference with respect to somewhere else. It's a potential difference. That's incredibly important, and it's probably the single most important lesson you'll get out of today in terms of handling a battery. If we say a voltage up here is 230 volts, that's with respect to something. So that's 230 volts with respect to this horizontal line. We have to define what that horizontal line is, and that's what many people will call ground. So if we say it's the ground, it's literally the ground. So in power stations, they reference the power to ground. They drive large, big metal stakes into the ground to provide something called an earth reference or a ground reference. So that means that for an AC power circuit, you're always touching the other side of the circuit. You're always touching the neutral wire or the ground wire effectively by being on the ground. So that means that if you've probably been told as a child, or hopefully as an adult, to never touch a live wire because you'll get electrocuted, you get shocked. And the reason is you're always in contact with the second wire. So when you touch the live wire, you complete that circuit and you're experiencing a potential difference between the live wire and ground. When it comes to DC systems, most batteries are not grounded. This would be quite uncommon. You've probably seen in many cases that a battery cell has a plus and a minus. So right now, I'm completing the circuit on this battery cell. I'm experiencing a voltage of 3.7 volts here. I'm not being electrocuted, but there is current flowing through my hand right now. It's just a really, really small current, because going back to our fundamental equation here of V is equal to IR, the voltage here is 3.7 volts, but the current is tiny because the resistance of my hands is probably 50,000 ohms or more. So that means that the current flowing through it is 3.7 divided by 50,000. So it's a really, really small current. And that's why you don't have to worry about it. But when it comes to higher voltage systems, let's say 230 volts, if this was me touching this, the current will be a good bit higher. And the reason when it comes to electrocution is that your heart, it can be stopped or prompted with small electric currents, typically 20, 30 milliamps, 50 milliamps, 100 milliamps. So that's 100 1,000ths of an amp is enough to stop your heart or potentially even lower. So that's why you have to be careful with high voltages that you don't touch them. But what's interesting when it comes to batteries and why batteries are intrinsically safe, and for example, this is the control box of one of our batteries. If this was real and energized, I could take off the cap here. I could touch and grab this if it was 1000 volts DC, and absolutely nothing is going to happen to me. You might ask, how is that possible? Why don't I get electrocuted? Because I'm not completing any circuit. Batteries are floating, and what that means is the negative or the positive, they're not referenced to ground. I'm standing on the ground. So if I touch positive, nothing happens. If I touch negative, nothing happens. If I touch both, I'm going to have a very bad day. So that's the big difference here when it comes to DC systems. And when it comes to safety, is that voltage is potential difference, the difference between two surfaces. So if you haven't completed the circuit, then you're going to be safe. That's totally different to alternating current that we use today. And you might wonder, why don't we use DC current everywhere today? Well, the reality is, up until probably a couple of decades ago, the easiest way to generate alternating current was from electric motors. And electric motors, they spin. So with an electric motor, it's spinning around in a circle, and it's basically got magnets on it in some machine designs. And as they rotate around in a loop, that's what you're seeing here. If you've got magnets here on the outside, so you've got an inner part of the motor that's spinning and the outer part of the motor that stays static, these north and south magnets, they try and repel each other, they try and push each other back. So as they're trying to push each other back, you're creating a higher and higher voltage. It's like compressing a spring, coiling up energy. So this was the easiest way to generate power, because electric motors and power plants are basically generators. It's the same thing. You have a steam turbine turning an electric generator that generates AC voltage, which can then be used to power loads. Batteries are fundamentally different. Batteries have a constant voltage output, and they're not able to generate energy. They only store energy and can discharge it out. And the reason we use AC power today is it's very easy to convert AC power from one size to another through something called a transformer. So that concludes our very basic overview of energy, power, voltages, and batteries. Thanks for listening, and I hope you found that insightful.